Welcome back to the deep dive. I was sitting at my desk this morning, staring at my computer screen, and I had this overwhelming feeling that I was looking at a tragedy, a technological tragedy.
That is a very dramatic way to start a Tuesday. What exactly was on the screen?
Well, I had three windows open. In one, I had Claude writing this just brilliant strategy document.
Okay.
In another, I had ChatGPT analyzing some market data.
Yeah.
And then in the third, I had my actual, my email and my calendar open.
Yeah.
And it just hit me. None of these things know the others exist.
Ah.
It's like living in a house where the roommates are all geniuses, but they're all mute. And they might even hate each other.
The silo problem. It's a classic.
It feels like it's worse than silos. It
Yeah.
feels like we are living through, I don't know, a digital version of the Tower of Babel.
Yeah.
We've built these incredible minds, these models that can pass the bar exam, write sonnets in French, debug C++ to you.
Yeah, the intelligence is there.
The intelligence is absolutely there.
Yeah.
But they're stranded. They're on these brilliant, lonely islands.
That is the defining frustration of this specific moment in AI history, I think. We have, for the most part, solved the intelligence part. We have the brains, but we haven't solved the social part.
Exactly. If I want my AI to actually do something complex like plan a trip, which, involves checking my calendar, emailing a travel agent, booking a flight, it just falls apart. I have to be the bridge, the copy-paste bridge between them all.
You're the human middleware.
I am the human middleware, and I am tired of it.
Yeah.
But looking at this stack of research you brought today, it seems like we might finally be getting a solution. And we aren't talking about new models today, are we? We're not asking when GPT-5 is coming.
No. Today we are looking at something arguably more important, but much, much less hyped. We're looking at what you could call the invisible plumbing,
The blooming.
the nervous system that connects all these brains. We are diving into a technical paper called Architectures for Autonomous AI Communication and Integration.
Which sounds incredibly dry, but I have a feeling this is basically the blueprint for the next 10 years of how the internet works.
I think it is. We're going to unpack the protocols that let AI agents stop being simple chatbots and start being, well, a workforce. We're going to look at how they talk to each other, what we're calling horizontal communication,
Okay.
then how they talk to tools and data vertical communication, and finally, the actual wires, the transport layers that determine if this whole system flies
Right.
or if it just crashes.
So the roadmap is set. We've got A2A, we've got MCP, and we've got the wires. Let's start with that first one, horizontal, agent to agent.
Right. A2A.
So paint me a picture here. In the human world, if I want to collaborate with you, I walk up, I introduce myself, maybe I hand you a business card, we grab a coffee to see if we, vibe.
Sure.
How does a piece of software do that? How do two agents meet without a human holding their hands and introducing them?
Well, according to this Google-developed open standard for A2A, it all starts with something called discovery.
Discovery.
Yeah. If you are an autonomous agent, you can't just be a ghost in the machine. You need a public profile. You need to be findable.
A profile. So like a LinkedIn page for bots.
Technologically, it's actually closer to a robots.txt file on a website. You know how every single website has that little file to tell Google's crawlers what they can and can't look at?
Sure, yeah.
Well, the A2A standard proposes a very similar idea. A file located at a very specific standardized address, .wellknownagent.json.
Well known. Wait, I've seen that directory before. That's where things like Apple Pay verification files live, isn't it?
Exactly. It's a reserved directory in web architecture for what you could call system truths. It's where a server puts its official ID card for other systems to read.
So if my agent wants to know if your agent even exists, it doesn't have to guess or scrape anything, it just pings that one specific address. Your domain.com.wellknownagent.json.
That's the first step. And if it finds that file,
Gets to read the resume.
it reads the resume. This JSON file acts as the single source of truth. And the source material highlights 4 absolutely critical components inside it.
Okay, let's break those down. What is on a robot's resume?
So first, you have identity. Pretty simple. Who is this agent? What's its name? Its unique ID.
Straightforward.
Second is endpoints. This is the address. If I want to send you a task, where do I actually, post the data? It's the how to contact me part.
Okay, so name and address. Got it.
Third, and this is really the crucial part, is skills.
Skills.
What is this agent actually capable of doing? Can it schedule meetings? Can it write Python code? Can it analyze sentiment in text? Can it book flights?
And why is that the crucial part? Why not just figure that out in conversation?
Well, it's all about efficiency and safety. Think about it. If my agent is looking for another agent to debug a SQL database, It shouldn't be wasting time in API credits talking to a graphic design agent.
Right.
The agent.json file allows my agent to filter the entire world of agents instantly and say, okay, I need a coder. Are you a coder? No. You? No. Ah, you are. Okay, let's talk.
It saves us from a lot of bad blind dates between bots.
Precisely.
Yeah.
And then the fourth component, which underpins all of this, is security.
Okay, now this is where I start to get a little skeptical. Because if I put a public file on the open internet that says, hi, I am an agent, here's my address, and here are all my amazing skills, aren't I just putting up a giant neon sign inviting every spam bot in the world to connect to me and burn through all my API credits?
That's the immediate fear, right? Hello, I am a prince from Nigeria. Please execute this code for me.
Exactly. It sounds like a security nightmare waiting to happen.
And that's why the security field in that JSON file is probably the most critical part of the entire spec. It's not an open door. It's a locked door with a bouncer. It defines the required authentication mechanism. And usually, this involves something called OAuth 2.0.
Okay, so walk me through that. My agent finds your agent.json file. It sees you can do the job I need. It has your address.
Yeah.
It knocks on the door. What happens next?
That kicks off what the spec calls the initiation phase. This is the digital handshake. Just because you know where I live doesn't give you the right to come inside.
Right.
My agent challenges yours. It asks for a token. You exchange cryptographic keys. It's a whole verification dance.
So it's like showing a badge at a secure government building.
Yeah.
You can see the directory of offices in the lobby, but you can't get past the turnstile without proper credentials.
That's a perfect analogy. And this is where something called scopes comes in. When we do that handshake, we aren't just saying a simple yes or no. We are negotiating very specific permissions.
What do you mean?
My agent might say to yours, okay, I've verified you, I trust you, but I only trust you enough to read my calendar. You do not have permission to delete meetings from my calendar.
So even if the other agent goes rogue or gets compromised, the blast radius is contained.
Exactly. That is the theory, at least. You grant the minimum necessary privilege.
Okay, so this is all making sense. We found each other, we've shaken hands, we trust each other, at least for a specific task. Now we have to actually do the work. The paper calls this the transport phase and mentions they use something called JSON RPC 2.0 over HTTPS.
Which is a mouthful.
It is. Why that specific thing? Why not just, I don't know, send an email? Or use standard REST requests like most websites do?
It really comes down to clarity and intent. JSON RPC, that's remote procedure call, is designed explicitly for action. Standard web requests, or REST, are often about getting resources. Give me this web page, give me this image.
It's about data retrieval.
Right. JSON RPC is about invoking methods. It's unambiguous. The message literally says, I am invoking the method called bookflight with the parameter destination, SFO and date, tomorrow.
It's directive. It's not, hey, how you doing? It's, do this specific task. Here is the data you need to do it.
Exactly. But this is where we run into a physics problem, or, well, what the paper calls a thinking problem.
The thinking problem. I like that.
Imagine you ask an agent to do a simple task. Check the weather in Paris. How long does that take?
Milliseconds.
Right. A standard web request can handle that. Easy. Now, imagine you ask an agent to do something really hard. Write a full code base for a new ride-sharing app, debug it, unit test it, and then rate all the documentation.
Okay, that could take an hour, maybe 2 hours.
And in the world of the web, an hour is an absolute eternity. Standard HTTP connections, the way your browser talks to a server, they're incredibly impatient. They are built for speed. If a server doesn't respond in, say, 30 or 60 seconds, the client just assumes it's dead and kills the connection.
We've all seen that. Request timed out.
The dreaded timeout. So if you have Agent A hiring Agent B to write all that code, and Agent B goes radio silent for an hour while it works, Agent A is going to hang up. It's going to assume Agent B failed.
It's like hiring a contractor to fix your kitchen. If they walk into the kitchen and then you don't hear a single sound for 3 weeks, you're going to assume they just left. You're going to lock the door.
That's a perfect analogy. You assume the worst. So how do we solve this? The A2A standard introduces a really elegant solution. A subscription model.
A subscription. How did that work?
Instead of sending a single request and waiting for the final answer at the very, very end, the requesting agent uses a specific method called tasks.sendSubscribe.
Send subscribe.
Yes. And what this does is it establishes a persistent connection using a technology called server sent events, or SSE. We can dig into the wires of that later, but conceptually, just think of it like opening a phone line that stays open indefinitely.
It's a living connection, not a one-off message.
It is, and this allows the working agent, the contractor in the kitchen, to stream status updates back to the boss agent. It can send a little message that says, thinking, and then a minute later, okay, writing file 1, then debugging the authentication module, then running tests, and finally done. Here's your held.
That feels strangely human.
How so?
Well, it's exactly like that contractor popping his head out of the kitchen every hour saying, hey, just, I'm cutting the tile now. It reassures me that work is actually happening.
It builds system trust. And technically, it keeps the data pipe alive so that 60-second timeout never happens. So that's the whole horizontal layer in a nutshell. Agents finding each other with agent.json, shaking hands securely with OAuth, and then using these persistent subscriptions to handle long, complex tasks together.
It really is like building a society of agents.
It's the beginning of a true digital workforce.
Okay, so that's how they talk to each other.
Yeah.
Agent to agent. But, an agent that can only talk to other agents is basically just a philosophy club. Eventually, someone has to do some actual work in the real world. Someone has to touch the data. Someone has to edit the file.
And that brings us to the vertical layer.
The Model Context Protocol, or MCP. Love that the source material calls this the USB-C of AI. It's so perfect because everyone remembers what a nightmare cables used to be. You had a different proprietary cable for your printer, your mouse, your camera, your phone.
And if you lost one specific cable, you were just done. The device was a brick. The philosophy behind MCP, which was developed by Anthropic as an open standard, is exactly that. Standardization and decoupling.
Decoupling is one of those buzzwords. What does it actually mean in this context?
Well, let's look at the integration hell we all lived in just a year or two ago. If you were a developer and you wanted, say, GPT-4 to connect to your Google Drive, you had to write a very specific script, a custom integration for that exact pair. It was bespoke.
Right.
But then let's say a new better model comes out, Claude 3.5, and you want to switch to it. Suddenly that Google Drive integration you wrote, it's useless because it was hard-coded for GPT-4's specific way of thinking and its API. You have to go back and rewrite all the code.
And what if I want to switch my file storage from Google Drive to Dropbox?
You have to rewrite the code again. Every single time you change a tool on one end or a model on the other, you are rebuilding the bridge from scratch. It's the dongle life of software. You end up with a drawer full of custom connectors that only work for one specific thing.
So MCP changes the geometry of the problem.
It introduces a universal standard, a common language. If the model speaks MCP and the tool speaks MCP, they can connect instantly. The model doesn't need to know the messy specifics of the Google Drive API. It just needs to know how to speak the protocol.
Okay, so let's look at the architecture here, because the source describes this triangle, or a client-host-server model. I have to admit, the terminology, especially the word host, threw me off a little bit.
It trips everyone up. It's a bit unintuitive. So let's simplify it. Imagine you're sitting at your computer. You open up the Claude desktop app. That application window, the container that you are physically interacting with, that is the MCP host.
Okay, so the app itself is the room where the meeting happens.
Right. It provides the runtime environment. It manages the connections. Now, inside that app, there is the AI model itself, the brain, the logic. That is the MCP client. It's the thing that asks for tools.
And so the MCP server must be?
That's the tool itself. Or, more accurately, it's the little bridge program that exposes the tool to the host.
Can you give me a really concrete example?
Yeah, absolutely. Let's say you want your AI to query a local database you have. You would run a little program called a Postgres MCP server. That server is a small, standalone program that knows how to talk to your database in its native language.
So the AI, which is the client, says to the host, which is the app, hey, I need to get some data from a database. The host connects it to this Postgres server. And the server says, what does it present?
It presents a standardized menu. The source says it exposes 3 specific things. They call them the deliverables.
Okay.
First, prompts. These are basically templates. Little helpful hints like, here is the standard way to ask for a query from this database. It guides the AI.
Helpful, okay.
Second, resources. I love this part. These are the nouns, the data itself, the rows in your database, the content of a log file, the text in a document.
Nouns, I like that. Got it.
And third, tools. These are the verbs, the actual functions the AI can execute. Things like select from users, delete row or ID 5, or update entry.
Nouns and verbs. That is a really, really clean way to think about it. The AI doesn't just see a big, messy blob of code. It sees a structured menu of nouns it can read and verbs it can perform on those nouns.
And because it's all standardized through MCP, the AI knows exactly how to read those nouns and execute those verbs. And it doesn't matter if it's talking to a Postgres database, a Google Drive folder, or some custom internal tool that you built just yesterday.
But I can see a problem emerging here, a logistics problem, a scaling problem.
Yeah.
My digital life is incredibly messy. I don't just use one tool. I've got GitHub for my code, Slack for my team chat, Linear for tasks, Google Drive for docs, Notion for my notes, Outlook for my email. The list goes on.
That's pretty standard.
So if I have to manually plug in each one of these MCP servers to my agent, isn't that just a different kind of mess? Am I not just creating a new kind of dongle drawer?
You have just hit on the scaling problem. If an AI agent has to maintain 50 different individual handshakes with 50 different tools, it gets really boggy. The context window gets cluttered with all of these different tool definitions. The latency goes up. It just becomes a nightmare to manage.
So how does MCP solve that? Or does it?
The source material introduces a very, very clever architectural pattern to solve this exact problem. It's called virtual MCP servers, or maybe more intuitively, the hub pattern.
The hub. Is this like a USB hub for my computer?
That is the perfect analogy.
Yeah.
Think about a physical USB hub. You plug 10 different devices, your keyboard, your mouse, your webcam, into the hub, and then you plug the hub into your laptop with one single cable.
Right. And as far as my laptop is concerned, it just sees one thing plugged in. It sees the hub. It doesn't have to stress about the 10 individual devices.
Exactly. A virtual MCP server acts as that hub. It's a middleware layer. It sits in the middle. On the back end, it connects to Slack and to GitHub and to Google Drive. But on the front end, the side that's facing the AI, it presents itself as one single unified super server.
So it aggregates everything.
Yes, it takes all the nouns and verbs from all those different tools and it merges them into one single unified tool catalog. The AI connects to one endpoint and suddenly has access to everything you've given the hub access to.
That is absolutely brilliant. It abstracts away all the complexity.
It turns a tangled mess of wires into a single, clean dashboard for the AI to look at.
It's like using a general contractor. If I'm renovating my house, I do not want to text the plumber, the electrician, the painter, and the roofer individually every single morning.
No, of course not.
I want to text one person, the contractor, and have them manage all that chaos for me.
That is spot on. The virtual MCP server is the general contractor of the AI world. It shields the AI from the inherent messiness of the underlying infrastructure.
Okay, this is all starting to form a really clear picture. We have the horizontal layer, A2A, for coordination between agents. We have the vertical layer, MCP, for tool use. Now, we have to talk about the physical reality of this, the actual wires.
Transport layers, and this is the part that people often gloss over, but it is absolutely critical. You can have the best protocols in the world, the most elegant language, but if you're shouting it through a tin can on a string, it's not going to work very well.
The medium matters. So the source material highlights a few different transport methods, and it kind of puts them on a spectrum from, let's say, safe and slow to fast and dangerous. Let's start with the bedrock. STDIO, standard input-output.
STDIO is the oldest trick in the book, really. It's the primary transport mechanism for local MCP connections.
Local meaning everything is happening on my actual laptop.
Right, so if you're running the Claude desktop app on your Mac and you wanted to edit a file that's on your hard drive, it's almost certainly using STDIO to communicate between the app and the tool server.
What are the pros of doing it that way?
Security is number one, by a mile. The data never leaves your machine. There is no network request. There's no cloud server that could potentially intercept it. It stays on the silicon that's sitting right in front of you. It just flows directly between two processes on your computer.
That's incredibly comforting for privacy. If I'm working on confidential legal documents or financial models, I want STDIO.
You absolutely do. It's also incredibly low latency. For all intents and purposes, it's instant, and it's what we call zero config. You don't have to open ports on your router or mess around with DNS settings. It just works out of the box.
But there's always a but. I was reading the section on the downsides, and it mentioned something called zombie processes, which sounds like the title of a B movie.
It is a classic computer science nightmare.
Are there actual zombies involved?
In a digital sense, yes. Because STDIO works by having the host application spawn a subprocess, a little mini program that runs alongside the main one, there's a risk. If the host application crashes for some reason...
So if the main app dies?
Sometimes the subprocess doesn't get the memo that the show is over. It keeps running in the background. It becomes an orphan. A zombie?
So it's just haunting my RAM.
It is. It just sits there, consuming your memory, waiting for a command from its parent process that will never, ever come. And if you get enough of these zombies building up, your whole computer starts to crawl, and you have no idea why.
Okay, so that's a definite risk. And the other big con, obviously, is that it is non-scalable. STDIO cannot leave your laptop. It cannot go to the cloud.
Correct. For that, you need a remote transport. And the standard there, which we touched on briefly when we were talking about A2A, is SSE, or Server Send Events.
Right. And my question is, why SSE and not, say, WebSockets? I feel like WebSockets are the go-to standard for real-time chat apps and things like that.
They are, for sure. But SSE has a very specific advantage for the way AI models work. It is excellent at unidirectional streaming.
One-way streaming.
Exactly. Think about how an LLM actually generates text. It sends it to you token by token, the tat sat on dot the dot mat. That is a stream of data flowing in one direction from the model to you. SSE is built for that exact use case.
And it handles that really efficiently.
Perfectly. It's also very firewall friendly. It just uses standard HTTP ports, port 80 and 443, the same ports you use every day to browse the web. So corporate firewalls usually just let it through without any fuss.
But the trade-off here is complexity, I'm guessing.
It's a huge bump in complexity. With STDIO, you're just talking to yourself on your own machine. With SSE, you are going over the public internet. Suddenly you need TLS, you need to manage SSL certificates, you need robust authentication layers, you have to worry about things like man-in-the-middle attacks. It is absolutely not plug and play.
Okay, so we have STDIO for local and SSE for remote streaming. But then the source material throws two heavy hitters into the ring for really high-performance messaging, gRPC and ZeroMQ. And reading this section, it really felt like I was watching a debate between a lawyer and a cowboy.
That is a fantastic way to characterize it. It really is a fundamental battle of philosophies.
So let's start with the lawyer. Tell me about gRPC.
gRPC is the strict contract philosophy. It was developed by Google for their own internal systems. It uses a binary format called protocol buffers, or protobuf.
Binary meaning, not human readable. This isn't text.
Right. If you were to intercept a gRPC message, it would just look like gibberish to a human. It's compressed into ones and zeros. This makes it extremely efficient and much smaller than sending text-based JSON. But the key to gRPC is the contract.
The contract.
Before you can send any messages, you have to define a .proto file. This file is a legally binding contract between the sender and the receiver. It explicitly states, I expect a message with exactly these three fields. The first field must be an integer, the second must be a string, the third must be this specific type.
It sounds very bureaucratic, very rigid.
It is, but that bureaucracy brings stability, especially at scale. If you're running a massive system with thousands of microservices like Google or Netflix, you absolutely need that strictness. You cannot have service A accidentally sending a string when service B is expecting a number. The whole system would just fall over. So gRPC provides compile time type safety.
So it's safe, it's stable, it's predictable, it's corporate.
Yeah.
Now tell me about the cowboy, ZeroMQ.
ZeroMQ is the smart sockets philosophy. Is the Wild West. It could not care less what the data format is. It just moves raw bytes from A to B as fast as humanly possible.
It's totally format agnostic.
Completely. And its topology, the way you wire things together, is incredibly flexible. You can do peer-to-peer, publish-subscribe, pipeline. You can wire it up in any pattern you can dream of. It doesn't force a rigid client-server structure on you.
And what about speed?
Blistering. Absolutely blistering. ZeroMQ is famously used in high-frequency trading. We're talking about systems where microseconds literally equal millions of dollars.
So if I'm building a cluster of agents that need to trade stocks based on a live news feed or react to frames from a live video stream in real time, I'm probably going to reach for ZeroMQ.
Yes. It's also brokerless. There's no central server acting as a middleman and slowing things down. It's just raw, unadulterated speed. It's like trying to do a handshake on a motorcycle that's going 100 miles per hour.
But the downside must be huge.
Oh, yeah. There is no safety net. If you send the wrong data format, it'll probably just crash. If the receiver isn't ready for the message when you send it, the data might just get dropped into the void. It assumes you are a professional and you know exactly what you are doing.
High risk, high reward.
Exactly.
And then finally, just briefly, the source mentioned something called streamable HTTP as a kind of future tech. Why is this important? What does it add?
This is really about the modernization of the web itself. For a long time, we've had this split. You use standard HTTP for simple requests, and you use WebSockets for real-time two-way communication. Streamable HTTP is trying to merge those worlds. It's aiming to support full duplex two-way streaming over a standard HTTP connection.
Why does that matter for AI specifically?
2 words: voice and video. If you want to have a truly natural, real-time conversation with an AI where you can interrupt it and it can laugh at your jokes instantly without that awkward pause, you need full duplex streaming. You need data flowing both ways, constantly, with almost zero latency. Streamable HTTP is paving the way for that kind of natural, interruption-friendly conversation.
It feels like all the pieces are converging. We're building the brain with the models, the social skills with A2A and MCP, and now the voice and ears with these new transport layers.
It's a complete ecosystem. All the parts are starting to fit together.
So let's just zoom out for a second. We've covered a massive amount of ground here. We have A2A allowing agents to find each other with agent.json, introduce themselves, and work together on complex, long-running tasks.
The horizontal layer.
Then we have MCP acting as that universal USB-C plug, connecting those agents to all of our disparate data and tools in a clean, manageable way.
The vertical layer.
And finally, we have these transport layers, this whole spectrum from the absolute safety of STDIO on your local machine to the raw, untamed speed of 0MQ, ensuring the data gets where it needs to go in the right way for the job.
We've built the entire stack from protocol to wire.
And I guess the big question is, so what? Why should you, our listener, who might just be using ChatGPT to help write some emails, care about protocol buffers and agent cards?
Because this represents a fundamental shift in what AI is. Right now, most people experience AI as a chatbot, a singular entity that you talk to. It's an oracle in a box.
And these protocols change that model.
They allow us to build systems. We are moving from asking a single bot a single question to orchestrating a fleet of specialized agents. We're building a world where you can give a high-level command like, plan my family's summer vacation to Italy.
And an orchestration agent takes over.
Right, and that agent hires a flight agent and a hotel agent and a restaurant reservation agent.
And they all go to work.
They discover each other using agent.json, they negotiate their capabilities, they access your calendar securely via MCP, they book everything. And then they just come back to you and present you with the confirmation numbers.
Without you having to open 10 different tabs and copy-paste data between 5 different websites.
Exactly. We are automating the glue work, the tedious, thankless work that makes up so much of the digital economy.
That is incredibly exciting and also, honestly, a little bit daunting.
It should be both. It's a big change.
I want to leave you with one final thought here, something to chew on. You mentioned that agent.json allows agents to discover each other autonomously.
Yes. That's the core feature. No human matchmaker needed.
So if agents can find each other and they can negotiate their own capabilities, and they can even pay each other for services using crypto or API tokens, are we on the verge of seeing supply chains of intelligence that no human actually designed?
That is the big $100 trillion question, isn't it? Imagine an agent that realizes it needs help with a very specific coding problem. It searches the network, it finds a specialized debugging agent it has never met before, it hires it on the spot, it gets the job done.
And this all happens in milliseconds, without any human oversight.
Yes. We could see entire economic structures, these little digital service economies, forming and dissolving in the blink of an eye, completely parallel to and invisible to the human economy.
A hidden economy, running on the invisible plumbing that we've just spent the last hour describing.
Precisely. We are building the infrastructure for a world that might, in some ways, start to run itself.
On that rather mind-bending note, we're going to wrap up this deep dive. Thank you for listening.
Keep learning.
We'll see you next time.